I want to tell you about exploring Mars with the European Space Agency. And as announced, I am the Mars Chief Engineer within the Directorate of Human and Robotic Exploration here at ESA. I am happy to take note of this 25th Annual International Mars Society Convention. I participated in the first convention 25 years ago, so this is a bit of an anniversary. So I want to give the attendees, can you all hear me okay? I guess so. We are ESA. What is ESA? The European Space Agency. Give a little bit of context since not everybody may be familiar. The European Space Agency is a little bit different than national space agencies. It is a treaty-based international organization with 22 member states and four associate member states and one cooperating state. Its objective is the exploration and use of space for exclusively peaceful purposes. We have 7 sites across Europe, and our headquarters is in Paris, and launches by the European Space Agency take place from French territory in French Guyana. Our annual budget is smaller than NASA's, is around about 6.5 billion euros per year. That amounts to 12 euros per European citizen. And we're hoping to increase that budget this year to take a step towards more European independence in space due to recent geopolitical developments. Nevertheless, it's a smaller space agency than NASA, and it has some differences. We do all aspects of space. We do communications and Earth observation and navigation. So the European Galileo system is done by ESA, not by a different agency. We do space safety, space security. We do operations and technology development, and we do exploration and discovery, science and exploration. And that's where the Directorate of Human and Robotic Exploration is housed. The Directorate of Human and Robotic Exploration, that's a little bit different, is we have Mars exploration in the same directorate at ESA as human exploration. And it means we can have synergies between lunar exploration, robotic and human, and Mars exploration, robotic for the time being in view of human in the future. What ESA has done at Mars in the past and what ESA is doing and planning for Mars in the future is what I want to tell you about today. We have a very productive scientific mission, Mars Express, that was launched in 2003. That mission has had its 19th birthday in space and has completed 18 years at Mars. Some of the things that the Mars Express spacecraft has done is contribute to the mapping of interesting landing sites, in particular, for example, the Jezero crater region, where the Perseverance rover of the Mars 2020 mission has landed and is collecting samples in view of the Mars sample return campaign. And the interesting clay minerals in the delta were identified by the Mars Reconnaissance Orbiter, but also by the Mars Express spacecraft instruments in orbit. Something more recent is because the Mars Express orbiter is not in an afternoon solar synchronous orbit, but is in a much longer orbit, it gets to view Mars a little bit differently and discovered these elongated clouds associated with our Siamons. They develop in the morning and move westward on the planet during the day, but generally have evaporated or disappeared by the early afternoon when the sun synchronous orbiters tend to cross over the area. So having a different view of Mars than all the other orbiters offers some interesting aspects and some synergies and some opportunities for better understanding the environment that we are all so enthusiastic about. The next spacecraft that ESA, the European Space Agency, sent to Mars was the ExoMars Trace Gas Orbiter, TGO, in 2016. The Trace Gas Orbiter has 4 scientific instruments for observing the Martian atmosphere primarily. 2 instruments, the NOMAD instrument, a spectral sounder that does solar occultation, and the atmospheric chemistry suite that also does solar occultation. The color and stereo imaging system, CASIS, and then a neutron detector, FRIEND. And those have been operating now since for 6 years at Mars. And they were looking for, primarily, the goal was to go and look for methane at Mars. And the Trace Gas Orbiter does not see methane. The Trace Gas Orbiter has put upper limits at 20 parts per trillion on methane in the overall atmospheric column. And what's interesting about this is that is in seeming contradiction to the observations at the surface by the Curiosity rover, which in Gale Crater sees values that are just below 1 part per billion. So a couple, within an order of magnitude, we're not even seeing that. That suggests that Curiosity is seeing things that are very localized near the surface and very transient and not globally representative. And as you can see by the many data points and observations from the atmospheric chemistry suite, and there are equivalent ones from NOMAD, there are upper limits that basically say that methane is not common in the Mars atmosphere at all. So Curiosity has found an interesting near surface locale. Likewise, there are upper limits, not explicit detections on other on ethane and ethene and other gases, which could be related to biological activity, or sulfur dioxide, hydrogen sulfide, which could be related to volcanic activity, and there are upper limits on those, but they're still searching if they find anything more locally emitted, but also not detected. What this is promoting is a lot of innovative chemical and dynamical modeling. So contributing to understanding Mars and realizing how curious Mars is, that there can be some things that are very local near the surface. One thing that has been detected is HCl, hydrochloric acid, in the Martian atmosphere. That is a detection, and that leads us to try to figure out how chlorine is cycling into the atmosphere. Chlorides have been detected on the surface, and so how do those things relate? How does the surface solid phase chlorides get mixed into the atmosphere? Or could there be an active volcanic source? This is a new branch of study to try and figure out how certain resources move around Mars, what their geochemical activity is. The Trace Gas Orbiter's color and stereo imaging system obtains imagery at 5 meters resolution with very consistent, excellent radiometric calibration. And the uniqueness of this particular imager is on the same orbital track. It does a look forward, and then the camera spins around to get stereo looking rearward to the track. So it can get essentially the stereo view of a given location pretty much through the same atmospheric column with the same radiometric calibration. And that means they get very good stereo capability that is competitive with and certainly synergistic with other stereo views, even at higher resolution by HiRISE on Mars Reconnaissance Orbiter. The imaging, the geologic research that's ongoing is with looking at active processes, landslides, polar seasonal processes, things we want to understand about what is happening on Mars today, and what that's telling us about modern Mars and linking to past Mars. There are those high resolution digital elevation models are available online. Then, what are we developing next at ESA? We're working on the Mars Sample Return Program in a cooperation with NASA and contributing several elements. A key element is the Sample Return, Earth Return Orbiter, which I'll tell you about. Another element is the Sample Transfer Arm that is part of the Sample Retrieval Lander of MSR. I'll focus on the main spacecraft, the ERO. It is a combined electric and chemical propulsion spacecraft that will launch from Earth, transfer to Mars, go into Mars orbit. At Mars orbit, it'll provide relay services for the surface assets of the Mars sample return program, and then monitor the launch of the Mars Ascent vehicle, capture the orbiting samples, and then depart Mars. This means that it will be the first spacecraft to do an interplanetary back and forth to Mars. And as you might imagine, that means this has to be a pretty beefy spacecraft. And so I like this next slide, which shows the size comparison between the Mars Sample Return Earth Return Orbiter that the European Space Agency is building and a Airbus 320 aircraft. We're sending a spacecraft to Mars and bringing it back at the end of this decade to bring the first samples back from Mars. A key element, a key technology required for that Earth Return Orbiter is electric propulsion. That is enabling. It means that we will be able to launch this almost 7-ton spacecraft on an Ariane 6 rocket, a European rocket, and not need higher performance because we will have the ongoing thrust, the continuous thrust between Earth and Mars from the electric propulsion. We will use a chemical propulsion stage for the Mars orbit insertion on arrival, and the electric propulsion then allows the mission phases of spiraling down and spiraling up and carrying out the rendezvous. It's based on heritage from the ESA Mercury mission, Bepi Colombo, and it's using 5 electric propulsion gridded ion thrusters. And we're spending a lot of time now on the qualification of those thrusters for the full lifetime requirements. As you could see in the previous slide, just jump back to that, with the almost 40-meter wingspan of the Earth Return Orbiter, there's a lot of solar power required to fire those electric propulsion thrusters. And that's why there are those really big solar arrays. And that is what is enabling to get to Mars and back from Mars. Again, it'll be the European Space Agency building the first spacecraft that goes back and forth to Mars. And then there's our much beloved and unfortunately further delayed Rosalind Franklin rover mission that is now proposed to go in 2028. The ExoMars Rover mission is unfortunately a bit of a victim of the Ukrainian crisis and current geopolitical situation. It was part of a cooperation on ExoMars with Roscosmos, the Russian space agency, and due to the political situation now and the sanctions, we have discontinued that the cooperation for that rover and surface platform mission, and are reconfiguring and are looking forward at the ministerial meeting that endorses every 3 years the ESA budget. That's this November. There's a proposal to rebuild the parts of the program that Russia was contributing, build those in Europe with some cooperation with NASA, and then launch in 2028 with a landing in 2030. And as I'll also show on the next slide, the scientific relevance of this mission remains because it is actually unique. The ExoMars rover landing site is unique. It will be the oldest ever, and it'll be the first mission that will probe the early history of terrestrial planets at this oldest landing site ever on the Martian surface, so older than the Jezero site where Perseverance is currently. What is also unique is the 2-meter drill capability, which will be used to extract and investigate subsurface samples. That is a much deeper drilling capability than any other currently planned mission has available, and that is demonstrated and qualified. And that will open a new window into Mars research as the best way to look for potential ancient biomolecules, potential evidence for past life on Mars, help us understand the context of the evolution of life on terrestrial worlds. And finally, with that sample from the subsurface, opening the third dimension of terrestrial planet exploration at Mars, we have already developed and qualified a unique integrated instrument suite that will be used. And it's conceived to its difference compared to the Perseverance and to the Curiosity rover is that the same sample will be examined by multiple instruments. It's not one sample provided to a single instrument. And that the rover is ready. It was tested, it was qualified, it was delivered. We'll have to do some maintenance on it to maintain it and make sure that everything is robust and ready for a launch in 2028. And I want to thank you all for your enthusiasm this morning, early for you, and see if there might be any questions from the room. I don't know if that's possible.
Okay, can you hear me, Dr. Haldemann?
Yes, I can.
Okay, I'm going to ask for questions. Any questions? All right.
Good afternoon, sir. Well, I presume it's afternoon where you are.
Yes, it is.
So you mentioned methane, and I know you're not the chemist on the spot, but do you have any observations from the instruments regarding the presence of superthermal electrons in the Mars environment as observed during the CSS flyby in October 2014?
There are indeed. Mars Express has been, I don't know about superthermal electrons, but Mars Express in 18 years has been observing the extended atmosphere and the space environment in and around Mars because of its larger orbit compared to many other instruments. And that information, it has detectors that have mapped the particles and fields in the near Mars environment. So there is information available that is coordinated also with the MAVEN mission. And there are some recent publications on that I know of. I don't have a slide today, I'm afraid. Another thing that is done to examine that by ESA is we're doing radio occultation measonements between Mars Express and the trace gas orbiter, and that is indeed sensitive to the ionosphere, the ionosphere of Mars, where there would be electrons moving around. And so those occultations, rather than being a single instrument on a single spacecraft, there are mutual occultations between those two spacecraft multiple times per day, and they're doing some observations every few weeks. So building up a larger database, that's been ongoing for the last year or 18 months, those mutual occultations. That took some time to develop that technique, and it's been productive so far.
Okay.
So I think I addressed your question without giving you a specific answer. I apologize.
You did. I've read the papers on the subject. I just wondered what you knew about it.
Thank you.
Yeah, this is Robert Subrin. I noticed that you're using this extremely large electric propulsion spacecraft to move a few kilograms of sample from Mars to Earth. Now, it's true that the electrical propulsion has many times the specific impulse of chemical propulsion, but the delta V to go from LEO to low Mars orbit and back to LEO with electrical propulsion is is 30 kilometers a second, whereas the delta V to go from low Earth orbit to Mars orbit capture with chemical propulsion is only about 5.5 kilometers a second, then another 1.5 kilometers a second to come back. So you've got a bigger exhaust velocity, but more than 4 times the delta V, and you're carrying this enormous weight of all these solar panels. It seems bizarre. Was there a requirement to use electric propulsion in this mission in order to please the electric propulsion constituency?
I don't believe that was the case, and I guess I don't. I'm not as quick as you, Robert, on the delta V math there, but certainly we did look at doing it all chemical propulsion, and that would have made it a much heavier spacecraft than the way we're doing it now. So we might have had smaller solar arrays, but the chemical propulsion needs for the delta V, which also includes some station keeping, lowering the altitude in order to capture and circularizing it. So the delta V indeed is lower for chemical propulsion, especially if you do aerobraking. But the timelines are not opportune for doing it that way. So we have the trades were all done. This really is a solution that now what there was a requirement for was to use a European rocket. And that indeed led us to the lighter weight option, which, yes, it has giant solar panels. But it is staged. As I said, there is a chemical propulsion element being used for the Mars orbit injection. But to have a chemical system available for the return was more prohibitive than the electric propulsion. If you're, I suppose somewhere there might be I'll have to track it down and I can send it to you. If there was I think a paper a few years ago doing the explaining the trade. Go ahead, next question.
Yeah, I hope this was easier. So could you describe the landing site a little bit more? Maybe I missed it, but is it in the southern hemisphere? Is it in the mountains? Is it more challenging to land on for that age? And then we all saw that the drill in our recent projects had some trouble, just like digging my backyard. They run into rocks. How are you avoiding that problem? How are you going to make sure that you get to the depth you want in your drill? So sort of a two-part question.
Okay, so two-part question. So the landing site for Rosalind Franklin is selected at Oxyaplanum. That if you search Rosalind Franklin landing site or ExoMars landing site, you should be able to find that explanation. We're not changing the landing site. It is in the lowlands. It is in the area of it's actually sort of north and east of where Mars Pathfinder landed. So it is at the mouth of an outflow channel, but in a exhumed area that has, by crater counts, older surface area, and it has clay mineral deposits that are of interest to the science team. So it's the landing site altitude and elevation as far as landing site, and it's also fairly flat. The landing site difficulty is commensurate with landing sites for other vehicles that have had landing ellipses of the order that ExoMars will have, sort of 100 by 30 or 40 kilometer ellipses, and that was already evaluated. The drilling, and I think you're referring to the difficulties in getting into the subsurface, that was encountered with the mole system, the HP3 on InSight, which is a very different system. It's not a rotary drill, but was a purely percussive self-hammering propulsion system to pull itself, if you will, into the subsurface. And it could not go around rocks. However, our drill does go through rocks. Very hard rocks will slow us down and take more power, but we have demonstrated that we can go into harder rocks. We do have a backup drill bit should that become necessary. We don't have a lot of drill bits, but we've tested and qualified the drill bit for the number of samples we expect to collect, which is 18 for the nominal science mission. So we've tested it with target soils also evacuated, so under Mars temperature and pressure in a big vacuum and cryogenic tube filled with dirt and soils and rocks and layered, and it works, and it collects samples. It's a little ripper mouth at the bottom is able to extract the samples. So we're looking forward to giving it a go on Mars. Sure.
I was wondering on the Franklin rover with the current Russian landing system off the table, is there any arrangements being made to replace that with a substitute?
That's the whole point. The proposal, which we're hoping will be endorsed by the Council of Ministers at the end of November, is that we build a similarly sized system to land Rosalind Franklin, build a similarly sized system in Europe. So we're starting from scratch. That's why it's going to take us till 2028. But we need to rebuild something. So we have now several of the elements in the landing system, in the Russian landing system, were already European. The onboard computer was European. The radar altimeter was the one that actually did detect the surface on Schiaparelli in 2016. We have inertial measurement units that are European, and those are going to be recovered and used for the system that we built to replace what was called the Kazachok lander. We're not loading any scientific instruments on it. We're going to keep it as simple as possible. So the only science we're taking is on the Rosalind Franklin rover.
Okay, thank you very much, Dr. Haldemann. And I appreciate your participation.
Thank you.